Let's just picture an absolute nightmare scenario for a second. You're tasked with writing a C program to store the ages or, I don't know, maybe the grades of 100 different students. Now, if you rely on what you've learned so far, you'd literally be sitting there manually typing out 100 individual variables in student 1, in student 2, all the way up to 100. It's clunky, it's totally inefficient, and honestly, it's a programmer's worst nightmare. You're going to spend way more time just declaring variables than writing any actual logic. So welcome to today's explainer, where we're going to put a stop to that madness and really demystify C arrays.
All right, so let's look at how the array basically swoops in as this elegant, single variable hero to save us from all that scattered box chaos. Instead of the sheer panic of tracking 100 separate variables, where you'd have to remember every single name just to do a simple math operation, you can achieve absolute zen. Just one sleek declaration. Int a bracket 100 bracket. Boom, done. With literally one single line of code. Using one unified name, you've instantly reserved 100 perfectly organized spots right in your computer's memory.
So here's our rescue map for today. 1. The 100 variable nightmare. 2. Inside contiguous memory. 3. Initialization tricks. 4. Accessing with loops. 5. The search operation. And 6. A quick coding challenge on min and max. Let's dive right in. Section 1. The 100 variable nightmare and the array solution.
Okay, so the absolutely crucial thing to grasp here is that an array is basically like a perfectly organized partitioned shelf. And the catch? Every single item on that shelf has to be the exact same data type. You really can't mix apples and oranges here. If you declare an integer array, every single slot can only hold an integer. Like our definition says, it's a collection of fixed-sized sequential elements stored at contiguous memory locations. Now that word contiguous, all that means is your data is packed tightly side by side, absolutely no gaps. And this matters immensely, because arranging data sequentially like this is the secret sauce that guarantees incredibly fast access speeds when your program actually runs.
Section 2. Inside contiguous memory.
To really wrap our heads around that speed, we need to talk about bytes. Remember that a standard integer data type dictates a very specific memory footprint. It typically takes up exactly 4 bytes of computer memory. So, when you ask the computer to store a single integer, it essentially blocks off a 4-byte chunk. If you ask for an array of 5 integers, well, the computer just maps out a continuous block of 20 bytes total.
Now, check out how that 4-byte footprint forces our data into this beautifully sequential byte-by-byte calculation in memory. Say our very first value, the number 5, is placed by the computer at a starting memory address of 1000. Well, the computer automatically knows the next element simply has to be exactly 4 bytes away at address 1004, and the next one, 1008. Because the memory is contiguous, the computer doesn't have to go endlessly searching your system for scattered data. It just performs this blazing fast mathematical jump to find exactly what it needs.
Section 3. Initialization tricks. Now, here is a truly brilliant shortcut. You can actually initialize an array without even specifying the size, and the C compiler will automatically count the elements for you. Notice how we left the square brackets completely empty here? We didn't type a 3 in there. But because we immediately provided 3 values in the curly braces, 21, 29, and 25, the compiler handles all the heavy lifting. It counts the items and just locks the array size at 3. It's clean, it's elegant, and it honestly saves you an extra step. But right here is where almost every beginner falls into a trap, so we really need to talk about the array index. Never ever forget this golden rule of programming. The first element is always at index 0, which means a 5-element array actually ends at index 4. I know, it feels a bit unnatural to start counting from 0, but it relates directly back to those memory addresses we just talked about. Index 0 basically tells the computer, hey, start at the base address and jump 0 spaces. So the first slot is 0, the second slot is 1, the third is 2, and so on. Moving on to Section 4, accessing elements with loops. Just imagine the absolute relief of not having to type out 100 separate print statements. Instead, we can use a loop to iterate through the array indices sequentially. It basically acts like our automated data scanner. So we create a for loop and set an integer variable, let's call it I, to start at 0, since that's our starting index. Then we set the loop to keep running as long as I is less than our total array size. Inside that loop, we simply say print array bracket I bracket. After that, the loop increments I by 1 and just repeats the process. Seriously, with just 3 lines of code, you can effortlessly access an array of literally any size. But consider yourself warned.
You absolutely must respect the boundaries of your array. If you try to print, say, index 10 in a 5-element array, C will throw an unexpected, completely random garbage number at you, or worse, give you a nasty out-of-bounds error. Unlike some other programming languages that'll kind of hold your hand and stop you from making that mistake, C assumes you know exactly what you're doing. It will calculate the memory address for index 10, jump right there, and print whatever random data just happens to be sitting in your computer's RAM at that very second.
Section 5. The search operation. So what if you have hundreds of array elements representing student grades? How do you verify if one specific grade, let's say an 89, is hidden somewhere inside that ocean of data? I mean, the computer doesn't have eyes, right? It can't just glance at the whole list and instantly spot it like we would.
To solve this, we utilize what's called a linear search. It's basically a systematic approach where we check every single slot one by one. First, we ask the user what number they're actually looking for. Then, we bring in our trusty for loop to traverse the array, starting right at index 0. Inside that loop, we use an if statement to ask the computer, hey, does the element at this current index equal our search item? The exact moment they match, we flip a found flag to 1, and we break out of the loop early, just to save processing time. Finally, outside the loop, we check our flag, and if it's a 1, we can proudly print element found.
All right, Section 6, a quick coding challenge on min and max.
Now let's think about this logically for a second. You can't see the whole shelf at once, so how does the computer actually figure out which number is the biggest? If you look at the very first box and it has a 10 in it, is that the biggest? Well, you honestly have no idea until you check the next box.
The genius trick here is essentially trusting the first element as your baseline maximum and then continually updating that baseline whenever you encounter a larger number during the loop. So we create a variable called max, and we set its value to whatever happens to be sitting at index 0. Then we loop from index 1 all the way to the end of the array. For every single slot, we ask, are you bigger than my current max? If the answer is yes, we just override our max variable with this new champion number. By the time the loop finishes running, the max variable is guaranteed to hold the absolute largest value. Oh, and bonus tip, if you want to find the minimum value, you do the exact same thing, but just flip that greater than sign to a less than sign. Simple as that.
I'm going to leave you with this final little trap to test your new skills. Can you spot the indexing error here? If an array holds 5 items and you ask the computer to print numbers bracket 5, what actually happens? Remember that golden rule. Arrays always start at index 0. So those 5 elements, they live at indices 0, 1, 2, 3, and 4. Asking for index 5 is stepping way out of bounds and just asking for trouble. So keep practicing these concepts. Write out a few loops on your own and ask yourself, if 1D arrays are just a single partition shelf, are you ready to conquer the wild, multi-layered matrix of 2D arrays next time? Stay curious and keep coding.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.